Hello, I'm Link, and this is my solution to question 2 of the 2023 CMO, or if you're looking at the Junior Olympiad instead, then this is actually question 4. So what this question says is we've got 20 students in a high school class. Each one has exactly 3 close friends. We start with 5 of them having tickets to a concert coming up, and if anyone sees that at least 2 of their close friends have bought tickets, then they're also going to get a ticket as well. And what we are interested in is it possible that the whole class buys tickets to the concert, where friendship is, of course, mutual? And if you start actually playing with this, you're probably going to pretty quickly come to the conclusion that no, this is not something that we can do. Just to get a little example of why, in case you haven't done this, I'm going to draw a little picture where I try to construct a situation where this happens as optimally as I can. So these are our initial 5 people. I'm going to call them nodes, just because this is kind of a graph theory looking thing. And they have tickets, so I'm going to call these active nodes and shade them in. For students that don't have them yet, I'll call those inactive nodes and just not shade them in until we activate them by giving them 2 connections with close friends who do have a ticket. Okay, yeah, and so in this drawing, I'm just going to kind of try to do this as optimally as I can. So now I've just activated all 5 of these guys. Everyone still has 1 connection that they can make, so I can do sort of another round of that. Drop each of these down, give it a connection from up here as well. So now everyone in the top 2 layers here has their 3 close friends already. There's nothing more that we can do there, and it's just the bottom layer that is left. So each of these only has 1 connection available, so I will just drop them down in pairs wherever I can. And that is all we can do. We do still have 1 loose connection coming off of this last student, so I guess we could put that to student number 20 in there, but we are kind of running into some issues because, well, I've done this as optimally as I can think of doing it, and not only do we not have every student in the class having exactly 3 close friends, well, there's no one left for this guy to connect to, unfortunately. We also only have 19 students who have tickets here. We only have 19 active nodes. But that's just the picture side of things. Let's try to convert this more into math now at this point. Yeah, again, we have if any student sees that at least 2 of their close friends have bought tickets, they will buy a ticket too. That brings to mind sort of an iterative process. And so I'm going to say, let's let each connection be kind of a step in our journey. And we have 3 options for things that we can do, 3 ways that we can connect things. We can connect an active node to an inactive node, a new inactive node, so one that has 0 connections. And in this case, it stays inactive, but we do have a bit more progress towards converting them, towards persuading them to get a ticket. We just need 1 more person to connect to it. Another thing that we could do is we could connect an active node to an inactive node that already has 1 connection. And so in this case, we actually get something interesting happening because this guy becomes active. Or, third case, there is 1 more thing we could do. We did not end up doing it in this example I drew because there just wasn't any space for it. I was trying to do this optimally, and this does not seem like it would be optimal, is we could connect an active node to another active node. And this doesn't really change a whole lot, it just kind of wastes its connections. Anyways, so we've got kind of 3 relevant quantities when we are looking at this process, and I'll just call those I'll give those little sequences names because we are considering this is like an iterative type of thing, right? I will call them NK, AK, and BK, where these represent after K steps, NK is going to be the number of available connections. And so what do I mean by that? Well, just to give the example of when we're starting, we have 5 students who are going to a concert. Have not assigned them any close friends yet, but we know each student in the class does have 3 close friends, so we can draw 3 connections off of each of these. And so in total at the start, we have 3 times 5 is just 15 available connections, ways that we can kind of connect these students to close friends. AK, I'm going to let be the number of active nodes after step K. And so again, at the introduction here, when we are just starting off, we have 5 active nodes with no connections made. So that's going to be 5. Whoopsies. And BK, I will let be the number of inactive nodes with 1 connection. It doesn't quite matter how many students in the class are inactive with 0 connections. Honestly, at this point, we can still kind of just consider it as like there's an infinite amount of inactive nodes with 0 connections, and we can just make a connection with any of them at will. But it is going to be kind of important which ones have 1 connection, because those are the ones that are going to turn into active nodes when we make another connection to them. At the start, we have none of these. We only have 5 active nodes and 15 available connections. All right. So good start. We've introduced our terminology here. Let's go ahead and convert these 3 actions that we can take up here into essentially like functions that we can run on these 3 sequences here. So let's say we have a tuple N, A, B in N3, where natural numbers I'm considering to include 0. Let's see what these 3 functions do, or these 3 actions do, to that tuple. So first action, remember, is we are connecting an active node to an inactive one that doesn't have any connections yet. Let's call this function f. What that's going to do is that's going to use up one of our connections here. It is not going to change the number of active nodes, but it will give us an inactive node that has a connection. So it is going to increase that b by 1. Second case, let's call this function g. What we were doing here, again, is we have an active node and we are connecting it to an inactive one that already does have a connection. So we have to spend a connection to do this, but by connecting to a new active node, which will now have 2 connections going to it, there's still 1 connection left there. And so we're actually introducing a new one. And so this cancels out and it just becomes n. We are increasing the number of active nodes by 1, and we are decreasing the number of inactive nodes with a connection by 1 as well. And lastly, in our third case, which we never actually saw, call this function h, we're connecting 2 active nodes. So that decreases the amount of connections by 2, actually, 1 for each node. We are spending 1 on both of those 2 nodes. It does not change the amount of active nodes, and it also does not change the amount of inactive nodes with connections. And these do also have some little domain restrictions. Obviously, these are all in N3. But if we want to run f, if we want to connect an active node to an inactive one, then we do need to have at least 1 connection. If we want to run g, then, well, This doesn't seem like it gives us any restriction, but we do have to make that connection. We're just also getting one back, and so we also need that n is at least 1. If we're connecting two active nodes, then of course we need n is at least 2. And of course we also need e to be at least 1 here. Technically we also need, there are kind of restrictions on active nodes in each of these cases as well, but we start with 5 of them and they can never go down, so that's not actually going to affect us at all. Okay, and now that I've gone through the trouble of going through domain restrictions and all that, I'm going to say let's just kind of ignore them, because it looked like if there is any sort of improvement to this process that I ran over here, it's probably going to be a very small one. I think I did that quite optimally. And so it's not likely that we can really get to 20 students or much more than 20 students, even if we assume infinite supply and we can kind of skirt these domain restrictions that we would ordinarily not be able to do. So having gone through all that trouble, I'm going to say let's just consider these all right now for our purposes as being maps, not from natural numbers to natural numbers, but from just integers to integers. So allowing negatives, allowing funky stuff to happen that would not work in this situation here. And what's nice is that under this domain here, all 3 of these are well defined, and importantly, they all commute with each other. So what that means is we can just run them in any order that we want. And that's great, because that's going to make it a whole heck of a lot easier to see if we can actually run this process the way that we want to run it. So we've already figured out here where our starting tuple is. When we begin this process, we have 15 available connections from 5 active nodes and no inactive ones. What is our goal? Well, our goal is 20 students in a high school class. All of them should be active. All of them should have tickets to the concert. So of course we should also have no inactive nodes because everyone in the class is active. Each student has exactly 3 close friends, and so we should have 0 more available connections as well. So available connections is 0, should have 20 active nodes, and we should have no inactive nodes. So by some sequence of steps involving F, G, and H, we want to transform our start tuple there into our ending tuple. But luckily it's really easy to compute what happens after some series of steps, because we can just rearrange the order, put them all together, and let's see what happens when we do that. So let's run F k1 times, let's run G k2 times, and let's run H k3 times, and let's take this big composition of functions and let's run it on our start position, 1550. What is this going to be? Okay, so just looking back up to reference our functions, each time we run f, we decrease n by 1. And so this is going to be 15 minus k1 because we're running f k1 times. G doesn't change it. When we run h, then we decrease it by 2. So we are going to subtract also 2k2 from that. For our active nodes, we are starting with 5. The only way that any of these functions can change that is with g. That can increase it by 1. So this is going to be k2. Whoopsies. Made a little mistake over here. That is h changing it, not g, and so that's going to be k3. And for inactive nodes, there's only, or actually no, sorry, there are 2 ways we can change that. When we run f, it goes up by 1. When we run g, it goes down by 1. And we start at 0, so this is going to be k1 minus k2. All right, and so that's what happens after running this sequence of steps on it, which we've just kind of like scrambled up to put all the f's together, all the g's together, all the h's together, right? All right, and now let's see if we can reach our goal like this. So what we want is 15 minus k1 minus 2k3 to be equal to 0. We also want 5 plus k2 to be equal to 20. I'm just kind of mashing coordinates over here. And we would also like k1 minus k2 to be equal to 0. This is a system of equations. It is a very nice and easy one. This one just says k2 is 15. So this one says k1 is equal to k2, which means k1 is also 15. Now over here, 15 minus k1 is 0. So negative 2k3 is equal to 0. And that gives us that k3 is equal to 0. So we shouldn't actually be running h at all. We should only be running f and g here. But that's kind of not what we wanted to see, is it? Because we have gotten seemingly an actual solution for this. That could be a problem. But let's think back to our example that we ran over here. What happened is that essentially we just would have needed to kind of invent a connection from nowhere in order to activate this node and make this final student purchase a ticket. And so that's going to give us a little bit of an idea to, okay, let's check out what the end behavior is. Another thing we could notice is that also we've taken a look at these domain restrictions, but not actually used those just yet. And so let's see if that affects anything. How can we get to the end here? We are not running any steps of h, so we are only actually using f and g over here. And in order to finish, well, we cannot have run f last because we're supposed to end with 0 inactive nodes. And so if we did that last, then we would have to have had -1 inactive nodes before that. That doesn't make any sense. So f does not work. And if we tried to run g on it, then, well, let's take a look at what happens. So g inverse of 0, 20, 0. Remember, this was the case where we connected an active node to an inactive node and turned it into an active one. The amount of connections would stay the same. The amount of active nodes would be 1 less, and we would have 1 more inactive node. So we have to have finished by taking g and applying it on this, essentially. But we have a problem. In order to use g, we need to have a connection to spare, because even though ultimately the amount of connection is not changing, we have to spend one before we gain one. And so this is not in the domain of g. And so what that tells us is that actually, even though we have this sequence of steps, this recipe that is supposed to get us that, that does not work under the domain restrictions of the actual physical scenario here. So we cannot get all 20 students to buy tickets. And that is problem 2 of this year's CMO.